This is my CHE 302 coursework 2 project, and it is on pseudopterosin. Right, so this is actually the structure of pseudopterosin, and they're actually a group of marine diterpene glycosides isolated from this specific coral here, which can be seen in the picture on the right. And they're mainly used for their anti-inflammatory analgesic properties, which means they are commercially found in skin creams as topical anti-inflammatory agents. This is the full synthesis of pseudopterosin, and as you can see, it's a very beautiful synthesis. However, for the interest of this project, I shall only be picking out 3 reactions which I feel most relate to our course, and throughout the next few slides I shall be further expanding on these 3 chosen reactions. This is my first chosen reaction. It is a Sonogashira cross-coupling reaction between a propylylic alcohol and a vinyl halide. This is done via the use of a palladium catalyst and a copper co-catalyst. The reaction itself consists of a coupling of the terminal alkyne with the vinyl halide. The Sonogashira cross-coupling offers a straightforward synthetic route with regards to stereochemistry. Thus, the formation of the sp2 sp bonds does not generate new stereocenters, which essentially means that the stereochemistry is retained throughout the reaction. Something to mention about the Sonogashira cross-coupling reaction is that it actually consists of 2 catalyst cycles, the first being the palladium and the second being the co-catalyst, the copper co-catalyst cycle, which I shall be looking at in this slide here. Now, the role of the co-catalyst in this case is to help facilitate the terminal alkyne preparation for the final product formation, which will be used in the palladium cycle. And essentially what happens is the terminal alkyne gets deprotonated and attached to the copper instead of the hydrogen. Walking through the copper co-catalyst cycle, we can see that the copper co-catalyst attaches to the propylylic alcohol and forms this pi alkyne copper complex intermediate. Now, why does this form? Well, we assume that amine is a base, and its sole purpose is to pull off this hydrogen proton from this complex. However, it is not a strong enough base, so DIPA is not a strong enough base. Therefore, the copper complex complexes with the alkyne in order to make the hydrogen more acidic, which allows the nitrogen with its lone pairs to remove this hydrogen. After this, the electrons help form a bond between the carbon and the copper, which we can see here. This can then be used in the palladium catalyst, which I will talk to you about in the following slides. So this is the complete Sonogashira cross-coupling catalytical cycle for this reaction. And before getting into the actual cycle itself, we just need to see how this palladium complex is prepared. As you know, we cannot use this complex as it does not have any coordination sites which we can attach our ligands to. So we need to convert it into this. And this can be done via ligand dissociation, which essentially turns this palladium complex into this. And this goes from an 18 valent electron system down to a 14. Note the oxidation state of the palladium does not change, and this has now got unsaturated coordination sites which can allow our ligands to bond to. Our first stage of the cycle is the oxidative addition, in which the vinyl halide reacts with the palladium catalyst in a way, with the palladium complex in a way which the palladium is actually between the bromine and the alkene. The next stage of the cycle is transmetallation, in which the carbon reacts with this palladium complex. The carbon from this product formed from the copper co-catalyst reacts with the palladium complex. We can actually draw this mechanism out as such. The carbon will attach itself to the palladium, removing this bromine. Now, why does this happen? Well, carbon will move to a metal group that has an electronegativity value closest to its own. Carbon's electronegativity value is 2.5 and copper's is 1.8, whereas palladium's is 2.4. With those results, the carbon is more likely to move towards the palladium rather than stay with the copper. This results in the formation of this product here, as the carbon has methylated onto the palladium complex for energetic purposes. Now, looking at this complex, we can see that the two phosphine groups are actually trans to each other. So, and for the next stage of this, or rather the final stage of the cycle, this is going to be a problem. So to overcome this, trans-cis isomerism occurs, where the two phosphine groups become cis to each other, making it easier to remove this group. And this is done in a mechanism as follows. And then apologies, this should be drawn as such. After this reductive elimination reaction has occurred, we now form the final Sonogashira product, and the palladium is then reduced back to its original state. This is my second chosen reaction. It is a synthesis of a tricycle, which can be seen here, and it uses a hydrocarbon and a nitroethylene molecule. And this undergoes a 4+2 diols alder cycloaddition. The hydrocarbon plays the role of the diene, and the nitroethylene plays the role of the dinucleophile. This is a good dinucleophile, as it has a strong electron withdrawing group, in this case the nitro group. Just some key points. In order to carry out the Diels-Alder reaction, the diene must be conjugated, which in our case it is, and it must also be in a cis conformation, which our molecule is. Looking at the mechanism itself, we can see that 3 pi bonds break, so the first one being here, second here, and third here. And this results in the formation of 2 sigma bonds. Now, this formation of sigma bonds is more energetically stable, which is a major driving force in the actual forward reaction. The mechanism itself is a pericyclic reaction, which essentially means that the bond breaking and bond forming all occur in one step, in one concerted step, which means there are no intermediates formed at all. The reaction itself is actually diastereoselective, as it forms a endo product over an exo. The exo is more stable, however, the endo product is favored due to by the kinetic controls due to the secondary orbital intermediates interactions, not intermediates. This can be seen here in the final product, where the hydrogen comes out trans to the nitro group when they fuse together. This is my third and final reaction, and it is a formation of a terminal alkyne. This happens in 2 distinct stages, which I will be going over, and the first is the Wolff rearrangement, and the second is a Peter olefination. This is done with the use of N-butyl lithium and trimethylsilyl diazonomethane on the THF. Sorry, with the use of THF. Right, so getting into the reaction, before we can actually start the mechanism, the trimethylsilyl diazone methane needs to react with the N-butyl lithium to create this lithium salt, which then can react with this croton aldehyde. So we can see that the silane attached with the metal attacks this carbonyl group, which results in a shift of electrons onto this oxygen, which leaves it negatively charged. The next stage of the reaction is where this undergoes intermolecular reaction called Wolff rearrangement, in which the electrons from this carbene forms a pi bond here, which results in this group breaking off. However, it reattaches back onto this carbon, and this results in this carbon-nitrogen bond breaking. Now, why does this break instead of this? Well, this is because the carbon-nitrogen bond is very weak, and this bond can easily be, or rather, it can much easily be broken compared to this. this results in the releasing of this nitrogen as gas. And something to mention is that all of this occurs in one concerted step, so no intermediates are formed. The next step of this reaction is the beta-olefination, and in this the electrons on this negatively charged oxygen are shifted onto this silicon, which makes a bond, as you can see here. Lastly, due to us using a base, sign elimination occurs, which results in the CO bond breaking, and this means that the trimethyl siloate is removed from this complex, and the electron from the carbon silicon bond is able to form a triple bond, which results in the alkyne production. This slide just contains all my references I have used throughout the PowerPoint.